focus of last week was the ensemble learning. Now, so what is ensemble learning? Ensemble learning, in a nutshell, is getting a whole bunch of different estimators and a whole bunch of different models and combine them together. And we find some interesting results that they can often increase the performance. You know, at the very least, it'll decrease the variance, and sometimes it can decrease the level of bias as well. And of course, bias and variance, those two concepts are something we'll talk about quite shortly. But the focus of today is your ensemble learning. So you're ensembling, or combining a bunch of models or estimators together. Cool. So the first, let me just move that here. The first thing I want to talk about is bias and variance, and the bias variance trade-off, if you will. So, let me just move that up here. Why is the mouse not reversed? No. Okay. Just click that. Cool. Yes. So let's use this here. Cool. So what is bias and what is variance, and why do we care about this? So when we have a model, and we use it to make a prediction on a specific data set, be it training, validation, or whatever, there'll be an error, right? There'll be, that can be measured a whole variety of different ways. You can measure it as mean square error. You can talk about it in terms of, I suppose, accuracy, or maybe, 100%, minus the accuracy. You can measure a whole variety of different ways. But the interesting thing is we can actually break down the error of a particular model, into a couple of different components. We have several components, and there's a bit of notation here, and I mean, you don't need to. I mean, I like to put it up because to me, it makes it a bit clearer. But you can just really I think in the slides as well, it just says error is approximately variance plus bias squared, right? So this is what's in the lecture slides, right? But the full formulation, if you will, I guess, or the more technical definition is this guy here. But you don't need to worry about that. This is all you really need to know, that your error of a particular model can be broken down into the variance and the bias, right? And so this is, I guess, the more mathematical, a technical definition. I mean, this is the same, the variance of the estimator. And so you recall our notation. So Y is the response or the target. The index is the observation number. So in this course, we're going from, I is equal to 1 all the way to n. So we're indexing the number of observations with n, and we're indexing the number of predictors with m. Or it's the other way around. Sorry, the other way around. We're going m observations and n predictors. I think that's the way it's usually done within this course, but sometimes it flips around. Either way, it's kind of arbitrary how you do it. Okay. And you'll recall that this pointy guy, I guess that little, pointy thing up there above the Y, that's the that just indicates it's an estimator. So you'll see that notation a lot in statistics. You have estimators for a whole variety of different things. So so when you have an estimate of your response or your target, what is that really? That's our model, isn't it? That's a model we've built. The model we've built is estimating what the response or the target should be, right? And this is just the expected value, so you can think of it as the average, right? So this is the average difference between the target and our model. In other words, you can think of it as the error, right? The average difference between our target and the model, that's the error. Cool. And well, this is just the same. It's a variance. So that's a variance. That's a variance of an estimator. The bias, and this term here we don't see in the slides, but this is something you'll see quite often in in stats and other sorts of places. It's this epsilon here. This is the irreducible error. So it could be from a couple of things. So it could be measurement error. It could be something unmodeled. It could be a data issue. It could be a whole variety of different things. We'll just see it as the error that we can't get rid of, right? So measurement error there, could be, say for example, I don't know, you're producing some model that predicts someone's weight based on height. It could be that your ruler is, or whoever's doing the measuring, of the height. Maybe there's something wrong there, right? And it doesn't matter if you have a perfect model. If that measurement, if that feature coming in isn't perfect, well, you're always going to have some, level of error within there, right? Something modeled. It could be, a data issue. Yeah. Or it could, or to an extent, it could just be, the inability for the model to capture. I guess, often things in real life are quite complex, right? And then when you simplify it down to say like a data table, there's going to be some information lost there, right? So this epsilon, that irreducible error there, it captures all that residual, that's left over, right? But you don't have to worry about it too much, but it is something to be aware of, right? Cool. But the focus of this week is really bias and variance. So let's talk about bias first of all. So bias is a concept that turns up in statistics, and often it's in relation to a particular estimator. You're trying to estimate something, and bias is if there is some inherent deviation from what the true value is, right? So this chart or picture, which you've probably seen many times, is a good example of it, right? So another way to think about bias is, if you had infinite data points, an estimator which is unbiased would give you the true result, right? If there's no bias, given infinite data, you get the true result. So you can kind of see what's happening here, right? So if you're trying to estimate something, in this case, you're trying to estimate, the center of the target, the red point, right? The bias is any inherent, deviations or, differences, inherent differences between, what you're trying to estimate. So you can see here, you're trying to estimate this red point here. Now, these blue points are our estimators, right? It's an estimate of this guy, right? You can see there's an inherent difference, that is the bias. The difference between this red and this cluster of blue points, that's the bias, right? So bias is, so bias is, I guess, an inherent difference between your estimator and the true value, and it could come from a variety of reasons, right? It could be that, and we've got it up here. It could be that the model is too simple, right? It could be that you've got such a simple model. An example could be maybe you have a linear regression, right? And you've only got, say, just a straight line, and an intercept. So you've only got two parameters, but perhaps whatever construct you're trying to model, is far more complicated than that, right? So, given that simple model construct, given that the model isn't flexible or complicated enough, it can never truly capture. What you're trying to model, right? So that could be one source of the error. One source of the bias. It could also be that the model structure isn't right. So I don't know. Here we go. Here's an example, right? So here's if you look at the chart on the left, here's another example of a potential source of bias, right? And the bias here is driven by a mismatch between the model and whatever you're trying to model, right? So here you can see a clear mismatch. The mismatch here is that we're trying to fit a linear relationship when this looks, it could be, I don't know, some sort of square root, or maybe even a logarithmic kind of shape. I'm sure maybe even a polynomial, with the right coefficients could fit that. But either way, we could probably all agree that it's not linear, right? So this is going to be a bias. It's going to introduce bias into your model. Okay, so bias, so your error can be reduced down to your bias and your variance. And your bias is the inherent difference between what you're trying to model and your model. That difference there. Okay. And again, as I say, another way to think about bias is if you had infinite data points and your model was completely unbiased, you'd get the true result. Cool. Now the other part of your error is variance. Variance in a nutshell is, how you can think of it as how stable your estimator is in respect to the data. So variance is how much your estimate changes given you change the training data, right? So you can kind of see here as well. So you can think of each of these maybe as a different model with its own specific data set, right? So your high variance models, right? And say this is data set 1, this is data set 2, this is data set 3, that's data set 4, right? Your high variance models or your high variance estimators, the estimate's gonna change quite a bit depending on your training data. So that's what variance is. But notice here that in general, I guess it's centered around the middle. There's low bias here, right? So there isn't some fundamental, structural difference between what you're trying to model. So between what you're trying to model and your model, right? Cool. So that's bias and variance. And yeah, you can see here, all the different, I guess, scenarios that can happen. So yeah, we've talked about this. So this one is a high bias. So you can see here there's an underlying difference between your models, your blue points, and the red point, I guess the actual data, or I guess a real life construct you're trying to model. There's a gap there. But you can see here that each of these models, each of these blue points are clustered quite closely together, right? This tells you that even if you change your data set, your estimate doesn't change too much, and so it's a low variance estimator. And you can work your way through all these, and you can convince yourself that this is low variance, low bias, and high variance, low bias, etc., etc. Cool. Right. So we have actually maybe I'll skim through all the lecture notes first. Cool. So we have bias variance trade-off, the decomposition. Yep. So the total expected error is Biasvariance plus variance. Talk about this. Okay. There's a couple of different ways to improve your bias variance trade-off, decreasing bias or variance or even both. And we'll talk about a bunch of these. So we've got regularization, we've got bagging, we've got boosting, right? So regularization, you may recall, is introducing a penalty to, introducing a penalty for model complexity, right? It's a way to simplify the model and prevent overfitting. So examples of regularization include, you have your regularized linear regression. So for example, you have your lasso regression and your ridge regression. So you might recall, so if I go lasso regression. So you might recall in your lasso regression, or you might recall your linear regression in general, you have your mean square error. You have a cost function that you're trying to minimize, right? And with your regular linear regression, it's just your mean square error or sum square error equivalent. You're trying to minimize that. Now your lasso, it adds the subject to, here we go. Yeah. I mean, there's a couple of different ways. I think so the way, here we go. Yes, the Lagrangian. Yeah. So there's a couple of different ways to express it. In the lecture slides, I believe they use this form, and this kind of I hope this reminds you of the concept of duality and the Lagrangian that we saw last week. If any of you have looked at that book, Introduction to Statistical Learning, they'll show you this form here, but they're equivalent. So if you look at this, this to you should look familiar. This first part of this expression here, that's the mean square error. So if you ignore this lambda and L1 beta norm here, this section at the beginning, that's just the sorry, excuse me, someone's knocking at my door. Hello, who's this? Hi, who's this? Hello? Hi, hello, who's this? dialed my apartment number. Hi, hello? Can you hear me? Sorry about that. I think they dialed the wrong apartment number. I have no idea who that is downstairs. Anyways, so as I was saying, this first bit here, that is your mean square error. So in your regular, not your regularized, your regular linear regression, you just be minimizing this. Now your regularized linear regression, we add this penalty term at the end. This is to regularize, or I guess, try and avoid overfitting by applying a penalty to your model complexity. So not only are you minimizing the mean square error, you're also minimizing the size of each of the coefficients, right? So what does that mean? Minimizing the absolute value of each of the coefficients, right? That's going to encourage the model to use less coefficients, use less parameters. The size of the coefficients are smaller. In other words, it's going to discourage overfitting, right, and encourage a bit of model simplicity. And of course, you can hyperparameter tune across this in order to find the the best lambda. So this is the regularization hyperparameter in your in this case lasso regression. Cool. So that's excuse me. So that is one way to increase your improve your bias variance trade-off. And I'll show you a graph which kind of, let me move that to the side here, which kind of shows this concept a little as well. Just trying to move that to the side. There we go. Hey, there we go. Cool. So what do we mean by improve the bias variance trade-off? Let me see. I've got a graph here which should show this concept quite well. Where did I put it? There's a really good graph I want to show you guys. Is it this one? No, it's not that one. I didn't put it in here. That's odd. I swear I had it in here. Let me quickly open up because I think it's quite good. Uni textbooks. Okay, so this is that book I was raving on about. I think it's really, really good book. I think it was at the top somewhere. I'll see if I can find it. There's a really good graph which demonstrates this concept of the bias variance trade-off. Bias variance trade-off. Ah, here it is. Perfect. Yes. This is exactly what I need. Okay. Okay, cool. So if you look at the graph on the right, hope you can know, this is the concept of bias variance trade-off and its relationship with flexibility. So we'll talk about this more a bit later, but you'll find that there's generally a relationship. As you increase the model flexibility or complexity, you will find that the bias will decrease, but it comes at the cost of increased variance. You can see it in this chart. So you can see this as model complexity, right? Or model complexity or flexibility. As you increase the flexibility, and you can measure in a variety of ways, this could be number of, linear regression parameters. This could be tree depth. This could be number of trees, say in a gradient boosting machine, just some generic measure of flexibility, whatever it may be. Notice what happens. So this is your mean square error here, right? This is your total error, right? And this total error is made up of the sum of your green line, your bias squared, plus your variance. Now you can see that there's an optimal point here, and let's assume this is on your test data set. There, that is the minimum. That is the point, the level of model flexibility or complexity where the mean square error is minimized. What do we notice? As we increase flexibility, bias is strictly decreasing. Look, it gets more and more. It gets, the level of bias gets less and less and less and less and less over time. On the flip side, you notice the variance increases, right? So you have two things happening, right? As you increase your flexibility, one thing goes down, one thing goes up. Now, what they're talking about before is, finding that optimal trade-off between bias and variance. Is you want to work out what level of flexibility gives you the optimal point. Because as I say, you increase your flexibility, one thing goes down, your bias, one thing goes up, your variance. You want to find out what the optimal point is. Now, this flexibility parameter here, let me just move this off to the side, this way. Yeah, this flexibility parameter here could even be this lasso penalty term, right? Although actually it's more the inverse, right? So you can use this regularization to find the optimal bias variance trade-off, which is what Geller is talking about here. Here we go. So 3 commonly used methods to find a good trade-off, right? So the first one, regularization. Okay, so what do we actually mean by find a good trade-off? What we mean is, this is the regularization part. This is what's regularizing your regularized lasso linear regression, right? What you're going to do is, you can think of this lambda as being on this x-axis here, or I guess the inverse of lambda, 1 over it, being on this x-axis here, right? So as you increase lambda, you go to the left, right? Because increasing lambda means the model is more simple, because you're penalizing complicated models. So you can think of, as you decrease your lambda, you're moving to the right, okay? So what you do is, in practice, if you're actually fitting a lasso model, is you vary this. You vary your lambda expression, and you work out what the optimal point is, right? In this case, it's here. So that's what Geller means by regularization. Bagging and boosting we'll talk about in a moment. Okay. Look, in the interest of time, I'm going to jump to the lab, and I'll jump back. I'll jump to the lab, and I'll give a bit more, I guess, flavor to each of the topics as they come up, and I'll see how we're done for time. If I have more time, maybe I'll go back to the lecture notes at the end. Cool. So this is our Jupyter notebook for today. It's talking about your bias variance trade-off in the beginning. I'll move this. Okay. So one of the first questions is, okay, so we have a model, we've fed it to some data, and the question is, okay, we've got all these concepts of bias and variance, which is all well and good, but how do we actually, detect this in our modeling? How do we actually, work out whether our model is, if there's a lot of bias, if there's a lot of variance going on with our model? There's a couple of different ways. I mean, it's not a precise way to do it, but there's a couple of ways you can get a feel of, whether the model is showing a lot of bias or showing a lot of variance. Okay, so with the first question, how can bias be observed in the estimation of error for a model? There's a couple of things we notice. Now, there's a relationship between bias and model complexity. So we find that your lower bias models tend to overfit, and I guess conversely your simple models or less complex models tend to underfit, right? So often the case it can be, if we see underfit happening in a modeling, it could be that we're using a high bias model. Maybe it's a little too simple. Maybe we want to use increase the model complexity, right? We can add more parameters, so we can add more in regression, we can add more, I guess, coefficients. Or in the case of decision tree, we can maybe make it a bit deeper. We can have a deeper decision tree. Or could even be switching to another class of models that is of a lower level of bias, but maybe comes with a higher level of variance. But how do we even detect overfit to begin with? Right? There's a couple of different ways. One way is, you'll see that, I mean, overfit's obvious. Overfit is, if you see your test or validation scores or error, is much worse than your training, then yeah, you're overfitting. It's likely you're overfitting to your training data set. Underfitting is a bit harder. It could just be a case of, if your test data, your score on your test data set, almost always will be worse than your training data set. Now, if they're really close, then you might be a bit suspicious, but okay, maybe I'm underfitting it. Maybe I'll play around, maybe I can increase my test slash validation accuracy or score by increasing the model complexity a bit, by, seeing if I can reduce the bias a bit, okay? So that's one way you can observe bias in a model. Often there's an underfit, right? Now here's another way you can go about doing it. This really you can only do in simple cases, right? If the dimensionality of the data is low. Now when I say dimensionality, I mean the number of columns is low, right? If there's too many columns, if you have too many predictors, it'll just take way too long to go through everything. But in a simple model, you can visually have a look and see if you are underfitting. Now, when I say simple example, I mean something like this. In this case, we have, for example, one predictor, right, and our response or our target is on the y-axis. Now, visually, you can see here. Okay, I don't even have to, do any fancy tests to see. Okay, this is underfitting. Clearly, the shape is, something a bit rounder, right? And this straight line here it's too simple. Actually, I think the homework 1 would be an example where you could, visually do some checks to see if you're underfitting, right? I mean, I don't think there were that many predictors. Correct me if I'm wrong. I don't think there were that many predictors. You can go through them one by one, have a look, and see how they're fitting. So that's a bit more of a judgmental manual way to see if you are, underfitting. Right. And the other thing is it changes little with new data. So you can see these are kind of two sides of the same coin. So why does it change little with new data? Because a low bias estimator, a high bias estimator typically, is also a low variance estimator. So you can also see, if our estimate isn't changing too much with new sets of data, we can infer, okay, maybe it's a high bias estimator. Okay, second question is, in our lab, how could the variance be observed in estimating? How can the variance of an estimator be observed? This one is aside from these two, which you can think of it as the the converse of this, right? That if you're given that bias variance is a trade-off, often you have your estimators will be high bias, low variance, or high variance, low bias. You can sort of see that as a flip side. So your high variance models will often overfit, which is sort of the, other side of the coin of here, right? Okay, and overfit, that's a bit easier to diagnose. As I say, if your test slash validation accuracy or cost is far worse than your training, then you're likely overfitting. There's actually another way you can ascertain the variance of your estimator. So when you do so hopefully you guys recall cross-validation. So just a quick summary, quick revision, bit of revision. With your cross-validation, effectively you're cutting your training data set into a number of, folds. So maybe 5, right? So you take your training data set, you cut it into 5 bits, and you'll train, on say 4/5 of the data, and then use 1/5 as your test set, and then you repeat that five times in all the possible ways you can cut it up, right? So you can actually look at, the standard deviation of each of those estimators, right? Because if you use, say, 5-fold cross-validation, you will have 5 models. And you can see, with 5, different sets of, data. Well, I mean, not entirely different, but 5 not entirely the same sets of data, how much it changes. And you can look at measures like the standard deviation of, the accuracy or cost or mean square error, whatever you're using to measure, your model performance by. You can look at the standard deviation of that as an indicator of the level of variance. Cool. Right, bias variance trade-off. So what are we doing here? So we're just loading up some packages. We're doing some linear regression. So I know it says polynomial regression here, but it's still linear regression. Keep in mind that linear regression means linear in its coefficients. So polynomial here, I mean, if you transform your predictors, your features, say you square it or cube it, that is still considered linear regression because the coefficient in front of it will still be linear in this case, right? So what do I mean by that? Maybe I'll make it a bit more concrete. So your linear regression equation could look something like this. Plus beta 1x. Okay. So this here is obviously linear. Now what if we had something like this? Oops. Okay, that wouldn't be linear regression because, again, linear regression. Linear in, I guess, the coefficients. That's well, all right. No. Not linear. Okay. Now if we have something like beta 0, of course you can replace the betas with thetas. I mean, you can use another Greek letter for your regression coefficients if you like. I think they use theta in the lecture slides. Cool. Yep, so this is linear regression. In fact, it's polynomial regression. This is effectively what we're doing here. So even though it's called polynomial regression, it's still a form of linear regression. Okay. So what they're trying to show here is the concept of overfitting and underfitting and high and low variance, right? So here, and they're trying to show the relationship. So typically a high bias model underfits, and typically a low, often a high bias model can underfit, and a high variance model can overfit. It's that duality, right, or that relationship, the bias variance trade-off. So you can see here that this is a high bias model. Why is it highly biased? Because there's an inherent, I guess, mismatch or deficiency between the model and what you're trying to model. So you can see here that there's a mismatch here. This is a straight line, and I mean the model we're using is a straight line, and clearly what we're trying to measure is not. What we're trying to model is not a straight line. It's not a linear relationship. There's a mismatch here. There's going to be that deviation, right? So this I hope you can appreciate has a level of bias. Remember our definition of bias, right? Sorry if that's a bit too small. So bias, when there's a fundamental difference between, I guess, what you're trying to model and your model. Could come from a variety of reasons, but yeah, it could be that the model is too simple. In this case here, the bias is caused by the model being too simple, right? In your linear regression, you've treated this as linear, whereas maybe you could have, done it as a polynomial, maybe some sort of square root. Maybe you could have, performed a square root transform on your x-axis, on your predictor before fitting your linear regression model. Or maybe you could have taken a log transform. This kind of looks like a log shape. Either or I'm sure would be fine. You can play around with it, maybe a cube root, whatever you can play around with and see what fits best. But yeah, so here it's a high bias model. There's a mismatch between the data and the model, right? But hopefully you can appreciate why this high bias model comes with low variance. You can imagine this line here, you could just play around with the dots a lot, like say, you got rid of this dot and moved it there. Maybe you move this dot over here. It's pretty robust actually to, the different data points. The model is so simple. You can kind of think of it as the way I like to think of it is this, right? So why does a more complex model create more bias? And why does a more complex model, reduce the bias? And why does a more complex model increase the level of variance? I think I wrote it out here actually. Where did I write that? Okay, this is how I like to think about it. Let me just make that a bit bigger. Okay, so what I'm trying to talk about is why is it that a increasing model complexity. Why is that increasing model complexity leads to higher, lower bias and higher variance? So this is how I like to think about it. This is more of a, I guess, a maybe intuitive sort of explanation. So when you make the model more complex, right, you can, real life is very complicated, There's a lot of things that can go on, and all these models, they're really simplifications of reality. As the inventor of the box plot said, I think his name is George Box, all models, again I'm paraphrasing, all models are rubbish, but just, some are useful. Okay, so a model that's more complicated, can, in theory, model or predict, a real life a bit better, right? Again, real life is very, very, very complicated. Okay, it's more able to, a more flexible, complicated model is more able to capture, the nuances of real life and data. But of course, this comes at a cost, because what you'll find is that when your model becomes more complicated, and I think it's easiest to think of this in terms of a decision tree, right? If you have a simple decision tree, maybe you only have a few splits, right? And if you have a few splits, each leaf node will have inevitably more observations, right? So again, let's say you have a simple decision tree. Let's show you an example. E.g., if you have a simple decision tree. E.g., let's say you have a data set of 1,000 observations. A simple decision tree, maybe there's, let's say there's 5 leaf nodes. Each leaf node maybe has, on average, 200 observations. Now, consider and this simple decision tree will have a high bias and low variance. On the flip side, you could have a complex decision tree, which is low bias and high variance, right? And maybe let's go crazy. Maybe there's 200 leaf nodes, right? And each one of the leaf nodes on average might have, say, 5 observations. Okay, so what happens here is that let's say you're trying to model something. If you only have 5 leaf nodes, if you only have a few splits, then you're probably not grouping things up, as well as you could, right? You're cutting your data, it's too high level, it's not granular enough, right? You're not splitting up your data into very specific buckets, right? You're sort of averaging everything out, you're smoothing everything out, right? So as a result, right, you're going to be missing a lot of the nuances in the real life data, but because each bucket is so big, because there's 200 observations, even if you change the data set, it's probably not going to move by too much. Now on the flip side, if you have a really complicated decision tree, there's 200 leaf nodes, maybe there's there's heaps of splits going on, right? Each split is very, very specific, right? So remember, another way to think about bias is if you had infinite data and there was no bias, then it'd be perfect, right? So with a complicated decision tree, let's say you have heaps and heaps of splits, you have like this exact kind of observation, then the bias is low because it's very specific. You're cutting it by that segment of the observation that you're trying to model, right? But the problem with all this is because you're cutting things so finely, because the level of granularity is so high, each bucket or each leaf node has very few observations. So hopefully you can appreciate, I guess with lower sample size, 5, if you swap out this 1,000 observations with another 1,000, the estimate's probably going to change by quite a lot. Okay, so that's another way to think about bias and variance, and why is it that complexity leads to lower bias and higher variance, and why is there that trade-off? So hopefully this kind of gives you a bit of a flavor or feel as to why that happens. Okay, cool. So we've talked about this guy. Now let's talk about the high variance and low bias model. Now hopefully you can appreciate here why it's going to be a high variance model. Now this model is so complicated, right? It hugs the data so tightly. It's in this case it's fitting to the noise. right? So you can imagine, right, if you move this data point from here to over there, the whole curve might, shift up, right? And imagine, worse still, imagine this one. This point here has a lot of, in regression, we call this leverage, right? And leverage, think about the layman's, I guess the everyday definition of leverage, right? This point actually has a lot of leverage over the shape of the curve. Why? Because it's the only guy out here and it's at the end of the curve, so you shift it up and down here, it makes a big difference. This point here has less leverage. Why? Because there's other points with a similar x value. So, if you're trying to predict, based off an x value of, say, I don't know, let's say it's 0.175, this might only have around a third of the weight, and, these two will sort of anchor it back here. But over here, if you're trying to predict something like 0.95, this is your only bet, so if you move this up or down, it's got a lot of leverage, a lot of pull. All right? And you can imagine that shifting any of these data points, in other words, if you replace this with another data set, it's going to change the curve by a lot. So it's a high variance model. On the flip side, this is going to be low bias. Why is that? Imagine you had infinite data points. Maybe there actually is a shape here, right? Maybe this is just a simplification. Maybe if you had infinite data points, it would actually look like there's a bit of curvature, maybe a bit of up and down. Real life maybe isn't so smooth like this, right? This can capture it. Even if not, even if the shape actually is, just a simple maybe logarithmic shape, a square root, if you had infinite data, this would all go away, right? Okay, so this is what this first example is trying to show. So it's just generating some random data, and it's just fitting polynomial regression scikit-learn model to it. So again, this is still a linear regression model. It's just that, the predictors or the features have been transformed into, I guess, a polynomial before we fit our linear regression. The next thing I want to talk about is your R-squared metric. Now, R-squared is a measure of model performance. It's a measure of goodness of fit. So I'm just trying to get this to the side. Doesn't seem to be working. Oh, there we go. Cool. No, it didn't work. I'm not sure. I'll just do it manually, I suppose. What's this? No, that's not the one. Okay, cool. All right, I had it out. Sorry about that. Cool. Yeah. So R-squared is so as I was saying, R-squared is a measure of goodness of fit. It's a measure of model performance. You can think of it as like something like accuracy or mean square error. It's a measure of model performance. Now R-squared, it generally lies between, I guess, 0, 1, where 1 is it can be negative if you have like an absolute rubbish model, I think, but generally it's between 0 and 1. So 1 would be, I guess, a perfect model, and I say perfect with quotation marks because perfect in this sense only means it just fit to the data, perfectly, right? And in regression land, the definition of R-squared is this guy here. So what this is this just tells, so SS total, that's a sum squared error of everything in general. So you can think of the denominator as, I guess, the total variance in the data, how much the data varies, right? SS reg is SS, or the sum of the squared errors explained by your regression model. So what this is saying is you've got your variance explained by a model divided by the total variance in the data. In other words, the total variance that is explained by your model, right? That is what R-squared is. So you can see a few things happening here with R-squared. Here you notice that your validation, your training score, it's actually quite similar. In fact, the validation one is actually better than your training score. So the red dots here are your training data, and the blue dots so the red dots are your test. The red dots are the test data points, and the blue dots those are the training data points. Now, yeah, the interesting thing here is, and this usually doesn't happen, your validation score is higher or is better than your training score. You're underfitting it. This is very unlikely unless you're underfitting. So this is another way you can kind of tell, right? So if your validation score is close to or worse, higher, better than your training score. On the flip side here, what do we notice? Your training score is quite good. Wow, it's almost a perfect fit. 98%, 0.98. It's fitting. And you can see why the R-squared is so high. You look at the data here, right? And it's hugging the data so tightly. This line crosses almost all the blue points. Maybe except here and that point and maybe slightly those points, but otherwise it's just fitting almost perfectly, right? And hence it's got an R-square of 0.98. It's quite good. Now then look at the validation score. It's absolutely rubbish, right? It's actually negative, okay? So maybe it's generally there, but you can be negative sometimes. Maybe that isn't quite correct. Now you can see why here, right? So over here, if you compare the line that were fitted, that model, to the red data points, it's quite okay. It's not too bad. It gets quite bad out here, though. Here's where it just becomes a bit outrageous. A bit of a rubbish model. Look at this. The prediction's all the way out here. That's a huge difference. And then you look at say this point, right? That's the actual data point, but predicted somewhere down there. It's quite deep down there. Actually, it's not even on the chart. And same with this point and this point. So here we've overfit to the data. And remember, overfitting is when you pay too much attention to your training data set such that it doesn't perform well on unseen data, as we can see here. Okay, so this is another way so this is what we were talking about before. One of the ways to detect the high variance model, which I talked about here. Yeah, so one of the ways to detect a high variance model is when there's overfit happening here. So, for example, this model here. Next thing I want to talk about is the validation curve. So you might hear it called another thing. So it's also called a learning curve. You might see it called a learning curve in places. Here we go. So essentially what it's trying to do is trying to find, I guess, the perfect level, the optimal level of model complexity. And model complexity you can measure in a variety of ways. So in decision tree land, you can measure it in terms of, say the number of, I guess, a tree depth, right? In linear regression land, you can measure it in terms of, say the number of parameters you're using. Or I guess with scikit-learn, the assumption is you use all of the parameters. But if you're fitting a linear regression model by hand, traditionally using maybe statistically, then the level of model complexity you can think of as the number of parameters, say your theta or your beta coefficients. In regularized linear regression, this model complexity here could be thought of as a penalty term, say in your lasso regression or your ridge regression, right? Other ways you can, in other sorts of models, say your support vector machine, there's that C penalty regularization parameter. So if I look up, say, sklearn SVM, that's C parameter. Okay, so this regularization parameter is the inverse of this model complexity here. So I guess as you increase the model complexity, your C goes down, right? Because you're regularizing less, right? So this validation curve here, effectively you're using it to try and find, I guess, the best level of model complexity. And of course you can each model, will have its own ways of thinking about your model complexity. But in general, you can see here that, on a specific training data set, as you increase model complexity, your error never goes down. As it becomes more complex, you're just hugging the data better and better and better. It's not going to decrease your score. But then, of course, on validation set, that's when you can pick up things like overfitting. And typically, you'd use a validation data set to pick the best model. So you can see here the optimum or the maximum is here. So you probably want to choose this level of model complexity. You can see it a little here as well. So if you can see it a little here as well. So you have a couple of different models. It's a little hard to see, but it's showing the what happens to I guess your mean square error as you increase your model complexity. Yeah, so this straight line here, that's your linear regression. That's this, I guess off yellowy kind of color here. It's the least, flexible. It's the simplest model. Then you have the blue line, which is it's kind of hard to see, but I think it's just this polynomially kind of shape, or simple enough polynomial shape. That's this guy here. And then you have the green, which is just like that, jagged. It's a little hard to see, sorry, my apologies, but then you have that green, which is that jagged sort of shape. That's overfitting, right, which is over here. Okay, and the optimal point is probably here. And sorry, the red, that's a validation data set, and the gray, that's a training data set. So we use the red, the validation, to work on optimal level of complexity. So it's this blue level here, which is again, it's hard to see, but I think the black line is really the blue. Okay, so this is, I guess, the validation curve in action. So this curve here is a validation curve. It's just flipped around because here you have model score, so higher is better. Here you have model error, so lower is better. So you can kind of think of it as just sort of flipped around. So if you sort of flip the y-axis around, then you effectively get something like this. So this is the same as this. But why I put this here was because you can kind of see it in practice. What do we mean by model complexity? And in this case, with linear regression, you go from, say, linear to, say, maybe this is a polynomial of order 4. I'm making it up. I don't know. I think it's order 4. And there's green one, which is maybe polynomial of order, I don't know, 10 or something way too much, or way too high, right? Something that's way too complicated. Okay. Back to our lab. So this is our learning curve here, right, and this is something I've been harping on about the whole time. Your high bias learner will tend to underfit, right? So high bias models are typically something similar, so it's not, it's too simple. It's not fitting closely enough to the data. On the flip side, your high variance learner will tend to overfit. So usually it's low bias. It hugs the data really, really closely, which can be a good thing, because if you hug the data really closely, it means that if you have enough data, you can get a really good model, because you're cutting things quite in quite a granular fashion. Cool. So then there's an example. Actually, I think there's one thing I forgot to mention about the RSquare. So this isn't part of the course, but something to keep in mind. So with RSquare, one of the problems with it is that it doesn't detect overfit. So if anyone's ever done any statistics or used linear regression before in a statistical context, not a machine learning context, one of the pitfalls of R² is that as you add more and more parameters, the R² can only get better. So then it can't pick up overfit. There's a few ways you can pick up overfit. Obviously, there's that machine learning, perspective, where we can use things like cross-validation. We can use things like validation sets to, detect overfit. In a statistical, from a traditional statistics point of view, there's other ways you can do it. There's statistical tests and measures you can use to detect it. But I won't bore you with this. But if you have any interest in statistics, there's other ways to do this as well. You don't have to use the machine learning perspective. Okay, there's adjusted R², which effectively is your R², but it just has a penalty for the number of parameters you have. So it sort of scales back. This R² depending on the number of coefficients, your thetas or your betas that you do have. Okay, but yeah. So this isn't part of the course though. Okay, decision tree. Now, decision trees are, notorious for being a high variance but low bias estimator. It tends to overfit. Now, why is this? Now, think about your decision tree. Effectively, it's a bunch of if-else statements, right? And using your if-else statements, if you grow the tree endlessly, you can affect it. If you can think of it in the extreme, the decision tree overfits the data the most. You could have, imagine a leaf node for every observation in your data set. I mean, that's crazy. That's obvious overfitting, right? But you can imagine if you have a data set of, let's say, 10,000 observations, you split that tree so much, you overfit so much that you have 10,000 leaf nodes. Now, what's the prediction for each of those leaf nodes? It's going to be whatever is in that leaf node, right? So if you have a leaf node in your decision tree, one for every observation in your training data, you're going to have perfect training accuracy. You're going to have zero mean square error. You're going to have perfect, a zero cost function, right? Now, that's clearly overfitting, right? Because once you move that, once you plug in, say, a validation or testing data set, that decision tree is probably going to perform quite poorly, right? So I hope you can appreciate why a decision tree is considered a low bias, high variance estimator. It's so flexible with those if-else statements. You can basically describe anything, but with great power comes great responsibility, as Uncle Ben from Spider-Man famously said. So we're going to use decision trees and other high variance estimators quite responsibly. And by responsibly, I mean, we've got to regularize a bit. We've got to, you do a bit of cross-validation. We've got to, control for overfitting. We've got to confirm on a test data set. We've got to be responsible and check on a test data set that we are not overfitting. Okay, cool. So I think we see this example here. So we have 1, 2, 3, 4. We have a multi-class classification exercise here. We have 4 different classes, and we're going to fit we're fitting a classification decision tree to this. Now you can see here, so this is a tree depth. This is the complexity parameter. So in the case of the decision tree, one way to think about the model complexity is, it's the number of splits. And hopefully you can appreciate why the more splits you have, the more complicated the model. Even if you think about, if you were to code up a decision tree from scratch, right? The more splits means you have more if-else statements. It's complexity. You can see what's happening as it becomes more and more complex and splitting it better and better. I mean, this is underfitting. I mean, if you look at the classification error, everything here at the bottom. Let me just make this a bit bigger. So if you think about here, so it's underfitting. If you look at the bottom segment here, this leaf node, this part of the branch here, everything is being predicted as purple, which is wrong, for a lot of the time. Say if it's green or blue, but we're essentially picking the mode. So the purple in this bucket, or in this bucket or this leaf, is the most popular. So the predicted value for this chunk here is purple. We split it again. I think it's quite good for green. Yellow is not too bad either, but it's not doing so great here. It's probably still underfitting. We probably need another split. Here we go. So this one's okay. I mean, I think it's probably it's arguable which one's better. I mean, this is probably overfitting a bit. I mean, this is probably underfitting. I mean, I'll probably say depth 3 is the best here, but I mean, I think there's a limitation of the decision tree here. If we were to segment this by hand, if we were to create a classifier by hand, it'd probably be something a bit smoother, maybe something like this, a boundary like this, maybe a boundary, like that and that. But of course, this is a limitation in the decision tree. So, one of these ones, this is probably underfitting, this is probably overfitting. Okay. But let's see what happens when we try to purposely create a decision tree that overfits. Okay, so here we have how many visualize tree max depth equals depth. What's the depth parameter here? Okay, I don't know how deep it's gone, but yeah. So you can see here it's trying to demonstrate a couple of things. So it's hopefully you can see by the number, I guess, rectangles or I guess polygons, you can see here that it's this decision tree here is quite deep. The max depth hyperparameter is not low, it's on the high side, right? And you could probably also intuitively see how it's overfitting, right? So I mean, look, it's got this cluster out here randomly that's purple, but then this guy here is green, right? It doesn't really make sense intuitively if you're to cluster these off. You're to create your own estimator by hand, right? Now these two are different data sets. This one's actually quite good, just I guess visually by inspection. I think it's just by chance. But the other thing it's trying to demonstrate is this is a high variance estimator, right? So this is effectively the same class or type of model. The only difference is we just plugged in a different data set. And you can see here the predictor has actually changed quite a bit, right? So this segment here is purple. Now you change the data set, and this segment here is green. Now, the predicted value that is. So it's a high variance estimator. Now, then the question becomes, okay, decision trees, they seem to overfit quite a bit. They're a high variance estimator. You know, they're low bias, which is great. But what can we do? How do we improve this? You know, how do we make our decision tree better? There's actually quite a few different ways. And hint, it's ensembling. It's ensemble methods, which is, I guess, the focus, one of the focuses of today's, I guess, tutorial or last week's lecture. Bagging is the first, I guess, ensembling concept that we'll talk about. Now, what is bagging? Bagging is short for bootstrapping and aggregating. Okay, let's break these down one by one. Let's talk about bootstrapping first. What is bootstrapping? Now, bootstrapping is a statistical technique. Effectively, it's sort of cheating, right? So, it's making an estimate by looking at your data and sampling from that with replacement to get, you know, lots of, I guess, fake or pseudo sets of data, right? So, say for example, you have an estimate of maybe say the mean. You're trying to estimate the mean of a specific data set using the sample mean, and you want to work out the standard deviation of it. So what you do is, if you're using Bootstrap, is you just take that, you know, calculate the sample mean on heaps of Bootstrap samples, then look at the standard deviation of what comes out. Yeah, but what I just said is not in this course. It's just a bit of extra statistical content. Just you know, you don't have to worry about that too much. But high level, bootstrapping, what it is a technique where you create pseudo data sets by taking a data set and sampling with replacement. And effectively, you know, you'd have sampling with replacement. That's the first part of bagging. The last part is aggregating, or you can think of it as averaging. Now, this is all well and good. Okay, so bootstrapping is, you know, creating pseudo data sets by sampling with replacement, and then aggregating is just chucking it all together and taking the average. Now, how does this relate to my decision tree? What does all this have to do with my decision tree? A couple of things. Oh, actually, let me give you a bit of intuition first, right? So now with we're going to talk about your bag decision trees. Effectively, what's happening is you are creating a whole bunch of decision trees using Bootstrap data. So instead of having, I guess, one decision tree, you might have 10 decision trees, all built using, you know, 10 different sets of Bootstrap data. Now, the data set going in is the same, but you bootstrap it to create, I guess, fake sets of data. Now, why does this matter? Now, in statistics, it's a concept, you know, like there's a bunch of concepts, one of which is, you know, intuitively, as you increase the sample size, your estimate should get better, right? Now, one example here is a toy example is, let's say you're trying to estimate, I guess, the mean number of children per family in Australia. I think it's like 2.5 or something. I hope you can appreciate that, you know, the more samples you take, you know, the better your estimate, right? It's going to have less variance, right? That's kind of what we're doing here with our bag trees. So instead of having one decision tree, we have, let's say, 10 or 20 or maybe 5 decision trees, and they all create an estimate, and then we average it all out, and that's our estimator, right? So it's relying on this concept here. But of course, you know, in an ideal world, we'd have 10 sets of data, but, you know, often our data is limited, right? So we actually, you know, use that. We recycle. Think of it as recycling. We have that data. You know, we're recycling that data and using it, you know, 10 times over just to create, I guess, more decision trees. Now, this is a formulation. This is from Introduction to Statistical Learning. Hope this doesn't confuse you too much. But what this is saying is, so f of x, this gives you the response or the target. And this hat is estimator. It means an estimator, right? So an estimate of the response for a given, I guess, a feature predictor. 1 on B, so B is the number of times in Bootstrap, so we're averaging here. And so effectively we're adding up all the bootstrapped estimates and dividing it by b. So this is the average of all the bootstrap estimates. So don't worry about the maths there. Just think of it as, you know, your bag tree is, you know, you bootstrap the data set, say 10 times. Each of those 10 times you fit a separate decision tree. Okay, and then you average out the results. Okay. Now what we find here is that when you do this, your bias is about the same, but your variance decreases, which is great, isn't it? This is another way to improve your model. You can actually apply this bagging technique to, you don't have to do it just in decision trees. You can apply it basically to any algorithm. The only downside, of course, is, you know, compute. You know, it's going to take more time and computing power and everything because you're fitting the exact same model, I don't know, 5, 10, 20 times, right? So bagging, this is an important point here. Bagging decreases the variance of an algorithm. Okay, you can read this in your own time, but it's just a bit of like stats about how this all works. Same with this. I mean, if you're so inclined, this is a bit of a, not really a proof, but it just sort of shows how and why bagging works. Yeah, and you know, why it decreases the variance. Okay, so yeah, if you're curious, you can look at this in your own time. But here's a practical example of I guess bagging in action. Okay, so here's a question. So here's our decision tree, and one of the things we notice is that it's high variance, isn't it? You change the data set and the model changes heaps. So that's what's going on in this, and what can we do to improve this result? Hint, bagging. Let's bagging, as we just talked about, is a way to decrease the variance of a model. Now the decision trees are notoriously high variance, so it's going to benefit quite a bit from something like bagging. I don't know if they're talking about bagging here. Maybe they jump straight to random. Okay, they jump straight to random forest. Okay, so random forest. Let me explain that. Once I can get my mouse over here. Okay, so bagging we've talked about. Let's talk about random forest. So one of the things about, you know, your bag decision trees is that you are taking, I guess, you're making pseudo data sets by bootstrapping. Now, the reason it reduces, okay, maybe I have to use a little bit of maths here. Okay, so a big part of the way bootstrapping works is okay, maybe this will confuse you, but there's a concept in statistics whereby when you take an average of something, right, when you're trying to estimate something, you take the average, the variance decreases, I guess, is inversely proportional to the sample size. Another way of saying it is that the higher your sample size, intuitively, the better your estimate. The higher your sample size, I guess the stability of the estimate, I guess the variance of the estimate, you know, tightens up, it decreases, right? Now, one of the things that it normally relies on, and normally we assume that, you know, it's independent. Now, the true formulation is here. There's actually a covariance term at the end. Again, I'd love to go through this in more detail, but I think it's just going to confuse a few people. But let me just put it simply. Your bag decision tree, it decreases the variance by averaging out a bunch of things. Now in statistics, when you average out a bunch of things, the variance decreases, okay? But there's actually another way to decrease the variance further. We do a handy trick in random forest. Effectively, we do the same thing as your bag decision tree, but then we add an extra step. Let's say we create 10 bootstrap data sets, right, from your original data set, 10 bootstrap data set. To each of those, we feed a decision tree, but we do something a little special. Each of those decision trees only gets a random subset of features from which to build a decision tree. So let me draw you out an example. So let's say we have, a data set. We have 10,000 observations. Okay, then we bootstrap. We create. Let's keep it. So let's create 4 bootstrapped data sets, right? Now, now to each of these, now we fit a decision tree to each of these bootstrapped data sets. So remember, the bootstrap was where we have we will also have 10,000 I guess rows, but they've been sampled with replacement from original data set. Okay, and then after we fit them, after we fit the decision tree, then we average out the predictions from all the bagged trees. This average forms our final prediction. Cool. Now this is I guess the method for your bagged decision tree. Your random forest is an improvement like this, and it does something a little extra. Okay, so this is the same, this is the same, this is the same. The only difference here, so random forest, what we do is each decision tree gets a random subset of features to build the tree from. Okay, now this is the key difference. This is the key point of difference between your bagged decision tree and your random forest. Now, why does this matter? It seems a bit random, right? Why we only give it a random subset of features? Now, why we do this is it decorrelates each of the trees. Oops. Okay. Now you can imagine okay, so recall the way your bag tree works, or the way that model works is when you take the average of a bunch of estimates, the variance decreases. But there's a link to the correlation, right? So if all the estimates are correlated, your variance reduction is not as much, right? So your random forest, it adds this extra step, the random subset of features to build the trees from. Now what this does is this decorrelates each of the trees. Now remember the variance reduction effect of the bagging method improves if the estimators, or in this case the trees, are less correlated. Okay, so this is the key point. Oh. So often this can improve the performance. Okay, so there's another way to improve the performance. So I guess in the grand scheme of things, random forests are often seen as more powerful than bagged trees, which in turn seems more powerful as decision tree. So I mean, decision trees, I'd say in practice they're not used. I mean, they are used here and there, but I mean, when your data set gets really big, when you have access to a lot of data and a lot of computing power, especially, people typically will use a more complicated model, a random forest or some other ensemble methods like boosting, which we'll talk about in a bit. Okay, so here we are using a random forest. Oh no, we do talk about the bag classifier. Okay, so this is the bag classifier. I think you'll see it's a little bit smoother. They've averaged it out, and I don't know. This to me looks pretty good. I mean, better than these two certainly. And with the bag classifier, if you change the data set, it will vary less the predictions. Here's a random forest. In this case, I think the random forest did an even better job. I mean, I'm sure you'd all agree that this clustering or this division or this classifier, looks better than this. Certainly looks a lot better than these or even these. Okay, so you can see that with the model improves. The random forest is the most complicated out of all these models, aside from boosting, which we'll talk about in a bit. But so when I say complicated, I mean previously before I said often when we increase the model complexity, we increase the level of bias. But these are methods that sort of they're neat in that it makes it more complicated, but can actually reduce the variance. So bagging is almost like a free, if you will, reduction to the a free improvement to the performance or reduction to the error. Well, not really free. You have to use more computing power, but in terms of the model structure, it's free. It doesn't cost you any bias. Maybe that's another way to think about it. So that's a random forest. It's probably the best model we have so far. You can also do it through regression. Here's a classifier. Did I talk about boosting? Okay, let's talk about boosting now. Oh, actually, there was one question in the chute. It was. Okay, question on random forests. What could we do to make use of multiple overfitting estimators to reduce the effect of overfitting? No, that's not it. Where's this one? Advantages of random forest. This is bagging. Oh, maybe they got rid of the question. Oh, no, here it is. Okay, cool. Yes. So what advantages does a random forest method have? There's a couple of them. So a random forest is, I guess, a type of bagging because you are bootstrapping and aggregating, so you reduce the variance. Okay. And the other thing is, is this comparing to boosting? Okay, yeah. Random forest is still relatively fast. It's simple. Now, one interesting thing about random forest is that boosting is one of the most popular and accurate. Yeah, it's one of the most popular and I guess powerful. Not most, but one of the more popular and powerful methods of building a model in the machine learning world. So, if anyone's ever heard of your Kaggle competitions, boosting is incredibly popular and has been used to win a variety of competitions. It's a great method. And it's used quite a bit in industry as well. So certainly where I work, so I'm in insurance pricing, in general insurance pricing, and that's used a lot. So GBMs and boosting are used a lot, and they can produce some pretty great models. But one of the downsides is that it's sequential. Now, of course, this only applies to your vanilla GBM. There's a lot of GBM implementations these days which you can make it parallelized. So there's something called XGBoost, which I highly recommend. It's a fantastic GBM implementation that can be parallelized and it's very optimized. But I guess in its vanilla form, GBM is boosting is sequential, and we'll talk about boosting now actually. So the last ensembling method we'll talk about today is boosting. Okay, so actually, there's other ensembling methods which are in the slides. You can just simply grab a bunch of estimators, average them together or take the majority vote. But I guess in the context of decision trees, here's some common, I guess, model-based, I suppose, if you will, ways of ensembling. Your bagging, your random forest, and your boosting. Okay, so what is boosting? Here's actually a simple diagram. Here's a diagram which kind of fleshes out the difference. So you can think of this as a single decision tree. You just fit one decision tree, and that's kind of it. Your bagging, you'd have this data set. You'd have multiple bootstrap data sets. It is all your pseudo data sets, right? And then you'd fit a decision tree to each of them, and you take the average. And of course, each one of these is independent of the other. So you can actually make this quite parallel. If you've got most computers are multi-core these days, so you can just fit several at the same time. And in fact, scikit-learn is really good about this. So scikit-learn, it's actually quite easy to use a multi-core, multi-threaded processing within scikit-learn. So if we go to sklearn, say random forest, it's really, really easy to fit something in parallel in scikit-learn. Threads. Is it here? Thread. End thread. End jobs. Here it is. Yeah, perfect. Here we go. Cool. So here's something handy. I don't know if you guys have played around with this, but if you're fitting any scikit-learn models, a large number of them have an argument. End jobs. You set it to. Just look at how many cores your computer has. I think I have. How many threads do I have? I think I've got 8 threads or something. I'm not sure. What does it say here? Who says here? How many threads do I have? Okay, so I've got quad core, and each of them are hyper-threaded or something. I'm not sure. I don't know what the terminology is, but all I know is I've got 8 threads. So in theory, I can run 8 jobs at once, or fit a model in parallel with 8 workers. Of course, the only problem is if you're doing something else, it might choke up your computer, and RAM might be a bottleneck. But yeah, that's something handy. You can use n jobs here, and with your random forest and your bagging, you can certainly use n jobs to make it parallelized. Cool. So boosting, what is boosting and how does it work? Boosting effectively builds a model sequentially, and it uses weak learners. For example, and a weak learner is just a very simple model, right? So one of the most common ways boosting is used is using, I guess, a tree stump. So that is effectively a decision tree with only a few branches, maybe 2, 3, 4, 5 branches, very small, stumpy trees. So the two types of, and there's also gradient boosting. Yeah, the two boosting methods discussed in the lectures. The first one is ADA boost, or adaptive boosting. So effectively what it does is you fit your first decision tree stump, okay? And then you look at the errors and you adjust the weights of your data set, okay? And then you go again, and then you go again, and you go again, and you could, in the end, you could end up fitting like 200, 300, 1,000 trees. You have many of these trees, right? Of these learners that you ensemble together, right? And each one will only be given a certain weight, right? Or a learning rate, which is talked about, which I'll talk about a bit more when I talk about your gradient boosting machine, which is another form of boosting. So so adaptive boosting. So both adaptive boosting and gradient boosting, you build your model sequentially, right? You build a stump, then you build another stump, then you build another stump, and you keep going, right? And each stump, I guess, looks at the previous, all the previous stumps to help train, right? So in ADA boost, you build your stump, and your next stump looks at the errors from the previous stumps and adjusts the weights. So you focus on the areas where you've been creating some errors, right? And you do this maybe 1,000 times. You aggregate it all together, and bam, you have your your boosted decision tree classifier, say, or regressor. Now, GBM, this is another form of boosting that they talk about. So this is actually from, I should probably say, this is from Introduction to Statistical Learning. I've copied this, I took a screenshot from that textbook, Introduction to Statistical Learning, that I highly recommend. So the algorithm essentially, it's sequential. So what do you do? So you start off with, I guess, a null estimator, and you do this, say, 1,000 times, 500 times, okay? And you look at your training data, okay, and you fit the tree to the entire training data set, right? But then you update this assignment. You update your estimator. You look at the previous whatever's there before, and you add this lambda is a learning rate. It might be like 0.1. So you give like you fit your first tree, right, and you give it a weight of 0.1, okay, and you update the residuals. Your residuals are the difference between your data, your observed value, your difference between the actual target values and your predicted target values, okay, and then you repeat. Okay, so you can think of it as gradually whacking away at the residual or the error, the difference between your data and your model over time, right? You fit your first decision tree, okay, and you give it a tiny weight. Say you give it a say 0.01, right? Okay, and then you remove that away from the residuals, okay, and you do the same thing, okay, and then the same thing and the same thing and the same thing, and you keep repeating this. So you are gradually whacking away. You're gradually chipping away at the residuals over time, okay? And so each of these will be a full decision tree given a weight of, say, 1/100. Okay, and in the end, here's the ensemble. Here's where you aggregate it all together. So GBMs are very popular. More specifically, if you ever do any machine learning, say in Kaggle or in industry, these are incredibly popular packages. XGBoost, CADBoost, LightGM, and they're very successful in Kaggle and other places as well. I use XGBoost a bit at work actually. I think it's quite good. But yeah, but these ones, these aren't this algorithm precisely. For example, XGBoost is a highly optimized version of this that allows for parallel processing. Because you look at this, you can't really parallelize it because it incrementally builds a tree on top of the previous trees. Cool. So that is boosting. Now, is there anything else left in? Let me have a look. Let me see if there's anything else left here. Okay, so the last thing is a talk about discussion about boosting. They're implementing boosting from scratch. I don't think you need to know that, but if if you are curious, you can go through the code. Yeah. So these are stumps. It is effectively a stump with one split. It's just it just has two leaf nodes. One split, one branch. Yeah, and it's looking at the misclassifications of the previous trees and building a new tree. And you can see each one is quite a bit different. What do we see above? We can see, the weak learners are one split. Each learner looks a little different as it tries to iterate and learn from the mistakes of the previous learner. Each individual learner does a pretty bad job, right? It's a stump. It can only be so good. But finally, in the end, it looks okay, The error drops down quite a bit. Yeah. Test data. Yeah. Cool. And in each of these, this is these colors. That's what the residuals left over from the previous training iterations. It's not the actual data, if you will. Cool. So I think that's all we have time for today. So I will upload all of this. I'll upload this video onto YouTube, and again, the files are in the Microsoft Teams file sharing mechanism. But so I hope you guys all have a good Easter break. I will see you online next week. And so remember, stay home, save lives. Let's all flatten the curve together, or keep flattening the curve. All right, good. I'll see you all next week.